Deterministic finite automata is a finite automata that recognizes regular languages. It's a machine that, given a language, accepts or rejects. So, going forward, we'll look at what an automata is. An automata takes a string at input and decides for that string whether it is accepted or is it rejected. So let's say you're given these two sample examples. You have this state which is called Q0. This arrow leading to Q0 indicates that this is your first state, which is also called your start state or your initial state. This is your starting point. Here you have a transition which goes out, leads back to Q0 with either an A or a B. And if you remember, our input letter or sigma is also A or B. So this comes back to Q0 with either an A or a B. Each time you traverse this transition, you can pick up either an A or a B. So every time you take one letter and come back to Q0. But the language for this DFA is the empty language. That is because Q0 is the start state, but this is not the accepting state. An accepting state is shown by a double circle this way. So here in this case, you're going from Q0 with, let's say, an A, and you're coming back to Q0. So the language or the string becomes the letter A, and similarly, any number of times you traverse this string, you can take either an A or a B, and eventually the language becomes sigma star. Let's go forward. Another example. This is the language of the empty string and the DFA for the empty string. So you have a state Q0 which is also your final state, where you have a transition leading away from Q0 and going to Q1, but Q1 is not your final state. Since Q1 is not your final state, anything that is reaching Q1 will not be accepted. Only all strings that reach Q0 would be accepted, but there is no transition leading to Q0. Hence, the only string that is accepted is lambda, which is the absence of anything. Now coming to another DFA, this is a Q0 to Q5 6-state DFA, where let's say you're starting with the initial state Q0, you're going to Q1, Q2, then Q3 and Q4 with the letters A, B, B, A. So the string that is accepted would be A, B, B, A. So let's say you have the string at the input tape. Let's see how it is traversed. With an A, when you read an A at the input, you go to state Q1. Then, when you read the B at the input, next, in sequence, you go to state Q2. Later, when you read a B at the input, using this B, you go to state Q3. And finally, when you have this A, you get to the state Q4. Since that is also a final state or an accept state, the last state determines the outcome, which is that the string is accepted. Now let's say your input string is ABA, not ABBA, but ABA. So here what happens, when you get this A, you go to the state Q1. When you get this B, you go to the state Q2. And when you get this A, you, instead of going to Q3, there is a transition leading from Q2, which goes to Q5. You get this A. And since your input is finished at this point, you see the state which you are at, is that an accepting or a final state? Since that is not, it is a rejection example. So the language accepted by this DFA is this one string only, which is A, B, B, A. So you see, although this is a 6-state machine, but the string accepted is only one in the language, which is A, B, B, A, as opposed to that we saw previously that there was only a 1-state DFA which accepted everything. Sigma star can be accepted by a one single state DFA. So to accept a string, the input string is read letter by letter, and state reached at the last letter is an accepting or a final state, then the input string is accepted. To reject a string, the input string is read again, letter by letter, and the state reached at the last letter is a non-accepting state. In that case, the string is rejected. So there are a couple more examples. Now let's say this is an example where the language has these 3 strings only. So if you see, your start state Q0 is also an accept state, hence accepting lambda. Then you're accepting the string AB. So you have an A here, leads to a non-accepting state, and a B here, it leads to an accept state. So when you take this path A and then this path B, you get to state Q0, you get to the state Q2, which is an accept state. So this string will be accepted. And similarly, the third string is A, B, B, A. So again, you start with the start state Q0, you take an A, you take a B, you take a B, and you take an A. So you need to get to the state Q4, which is an accept state. So that is good enough. Now let's formally define DFA. So DFA is part of is a combination of these 5 things. Q is a set which indicates the states. Sigma is your input alphabet, which does not have lambda. Lambda is the absence of an input alphabet, either an A or a B. Then you have rho, which is the transition function. This indicates how you go from a state X to a state Y with a particular letter. Then you have Q0, which is designated conventionally as the initial state, and F is a set of final or accepting states. So given this example, in this example your states are Q0, Q1, Q2, Q3, Q4 and Q5. So the Q set has these 6 states. Then sigma is AB. Note that lambda is not part of sigma. The input alphabet never contains lambda because that is actually the absence of either an A or a B. Lambda is not an input alphabet. So Q0 is your initial state. Q4 in the example is your final state. And your transition function is a general pattern is that all the states in Q into sigma, that is your leads to another state from Q, is your transition function. So let's say the transition function is something like this, that you have a state Q, you have the input X, you go to Q dash. This is a general description. Let's get to a specific example. So our transition function says that at the state Q0, if you get an input A, you go to state Q1. So at the state Q0, when you get the input A, you get to state Q1. Similarly, at the state Q0, if you get the input B, you get to state Q5. Here I would like to tell you something which makes it deterministic. Please note, coming back to the language for the empty string, please note here that you have the state Q0 and you are taking either an A or a B and going to state Q1. Why do we need this transition for the language of the empty string? That is because our sigma has 2 letters, an A or a B. So the idea is of a deterministic finite automata that whichever letters you have in your sigma have to be completely part of your deterministic finite automata. You have to have all transitions for every input letter leading out from every state. So you have a state Q0, and the state Q0, you have to have a transition for A and you have to have a transition for B. Although the language is lambda, but let's say you get an A, what will you do in that case? So you have to tell that you're leading to the state Q1 if you get an A, and similarly you're getting to the state Q1 again if you get a B, although the language is lambda. So similarly at the state Q1, you have to tell that regardless of what you get, either you get an A or you get a B, you are going back to state Q1. So you are actually telling that no matter what input comes, you will read the entire input and then decide whether it leads to an accept state or a reject state. That is the part which makes it deterministic. You can determine for every string, you have a determined path for every string, for reading every string. So that is about it for this part 1 of deterministic finite.